Hello there, Mr. Sutton here, bringing you the BC Calculus 712 Extra Practice Number 2 solutions on limit comparison test. On this problem, trying to figure out the convergence of this series. So this one, if you use the nth term test, you're going to see this does go to 0, but that doesn't really tell us a whole lot. The key on this one is recognizing that this is actually pretty close to 1 over radical n, which we know the convergence of. So I'm going to start by comparing this to that series, 1 over root n. Now this right here, this comparison series, the nice thing about this is a p-series. It has a p-value of 1/2, and since that's less than or equal to 1, this comparison series diverges. So there's a pretty good chance that the original series is also going to diverge. What kind of comparison test should we use, though? Because the original series has a denominator that is larger than the comparison, that means all the terms of this series are less than the comparison series. Showing that your series is smaller than a diverging series doesn't really prove much. So direct comparison is not going to help here. So we're going to go with limit comparison instead. So to start that process, now that we've got our comparison series all mapped out, we're going to show that the original and the comparison series are both positive for all n greater than or equal to 1. And at this point, we just need to take the limit of the original over the comparison series. So I'm going to let that be represented by L. I'll say L equals limit as n approaches infinity of original series over comparison series. Same change flip. We've got radical n over radical 3n plus 2. And then as n approaches infinity, this is really just, we can forget about this 2 down here. So this is just radical 3n, which I can rewrite as radical 3 times radical n. Canceling out those n's, we end up with just 1 over root 3. Now, since this is somewhere between 0 and infinity, I mean, there's a lot of wiggle room there. That shows us that, and also because our comparison series diverges, that shows us that our original series is going to diverge by the limit comparison test. To figure out convergence or divergence on this series, since this doesn't really fall into any of our easy categories, we're going to try comparing this to a series that we know the convergence of. So this is pretty close in behavior to n over n squared. And that series is really just simplifiable to 1 over n. Now we know the convergence of this one, namely that it does not converge. This is the harmonic series, which is known to diverge. So there's a pretty good chance that the original series also diverges, since it's going to behave similarly to this one, just the way the exponents shake out. In order to prove this, though, what kind of comparison would we use? Well, since the original series has a denominator that's larger than our comparison series, that means that the original is smaller than this diverging series, so direct comparison is not really going to help. Instead, we're going to use limit comparison. So let me start by saying that my original series is greater than 0, and so is this comparison series for all n greater than or equal to 1. And then let me take the limit of my original series divided by my comparison series, the harmonic here, and let's see what this limit comes out to. So same change flip, we've got n times n in the numerator, which is n squared. In the denominator, I have 3n squared plus 1 times 1, which is just 3n squared plus 1. As n approaches infinity, we can forget about this 1. So this is really just n squared over 3n squared, which if I cancel out those n squareds, is just 1/3. Since this is between 0 and infinity, that means that by the limit comparison, our original series is going to diverge just like the comparison series. On this one, we're trying to figure out whether this series converges or diverges. There aren't really a whole lot of techniques we have that can quickly unlock this one. If you try the nth term test, you're going to see that this does go to 0. It's not geometric. It's not quite a p-series, and it's not really something that looks like it would be easy to use the integral test on, although we might be able to do some kind of substitution to integrate this. So we're going to try comparing this to a series that's a little easier to find the convergence of. This ought to be very similar in behavior to the series 1 over n radical n squared. So basically same series, but without this minus 1 in there. Now this series can be simplified if you square root that n squared to just n times n down there, so 1 over n squared. And this series, this is just a p-series with a p-value of 2. Since that p-value is larger than 1, we know this series converges. So we would like to compare these two series and show convergence for this one then. In order to do that, though, direct comparison is going to be a little tough. Since the denominator down here is smaller than the comparison series, that means that this fraction is bigger than the comparison series. If you're bigger than something that's converging, that doesn't really show a whole lot, so direct comparison is not going to work so well here. So we will go with limit comparison instead. Let me start by showing that the original and the comparison are both greater than 0, and that's going to be true for n values that are greater than or equal to 2. So for greater than or equal to 2 n values, this is always going to come out to a positive number, because you're with 2 or greater, you're getting past the weirdness of having something smaller than 1 minus 1 inside that radical. And this is certainly going to come out positive. So all that's left to do, once we've shown this little precondition, is take the limit of the original divided by the comparison series. So I have limit as n approaches infinity of the original series here over my comparison series, which I'm just going to use the simplified version of 1 over n squared for that. Same change flip, I've got n squared over n radical n squared minus 1. And as n goes to infinity, I can forget about this minus 1. So I just have the square root of n squared, which is just n. Multiplying that by the other n, I get n squared down there. And then those are going to cancel out to give me 1. Since 1 is between 0 and infinity, this proves, by limit comparison, that this series is going to converge, just like the comparison series converges. To figure out whether this series converges, we first look to kind of our easy cases. It's not geometric, it's not a p-series, at least not the way that it's written here, and definitely not alternating. Nth term test, this just goes to 0 if you take the limit at infinity. So what else is there? The integral test on this one would actually work. I mean, if you split this up into n over n squared minus 1 over n squared, you could integrate that fairly quickly, but it would be even faster probably to compare this to a series that we do know the convergence of. This is going to be pretty similar in behavior to the series n over n squared, because that series is really just 1 over n, which is the harmonic series, which we know diverges. So there's a very good chance that this other series also diverges. We just have to come up with the right comparison test to prove it. Well, which comparison test would we use here? Since this series is smaller in the numerator, that means overall it's going to be smaller than the harmonic series. But showing that your series is smaller than a diverging series doesn't really help if you're using direct comparison. So we're going to use limit comparison instead. To do that, we need to show that the original and the comparison series are both positive for some n value. So if we plug in an n value, let's say greater than or equal to 2, then this series here, if you're starting with an n of 2, this is going to come out positive in the numerator and denominator, so it'll be positive overall. And the harmonic will certainly be positive if you're plugging in any positive n values. So for n greater than or equal to 2, these are both positive. So all we have to do at this point then is just take the limit of the original divided by the comparison series. So I'll use limit as n approaches infinity of, now I've got my original, and dividing that by my comparison series, 1 over n. This limit is going to, let's see, if I rearrange things, same change flip, this is going to be the same as we have n times n minus 1 in the numerator. And in the denominator, I have n squared times 1, which is just n squared. As n goes to infinity, I can ignore that negative 1. So I really just have n squared in the numerator as well. And that's just 1 if you divide n squared over n squared. Since that comes out to something between 0 and infinity, that means that the original series is going to have the same behavior as the comparison series. Since the comparison series diverges, the original also diverges by the limit comparison test. On this one, we're trying to figure out whether the series converges or diverges. This doesn't really fall into any of our easy categories. I mean, I know that 1 over radical n is a p-series that I know a little bit about. This isn't quite that, but we could actually compare it to 1 over radical n. So that'll be kind of our starting point here. Now, 1 over radical n, that's going to be a p-series with a p-value of 1/2. Since that's less than or equal to 1, we know that this p-series here is going to diverge by the p-series test. So that means that this original series, which is going to behave pretty similarly to this because it's got the same power, this original series probably also diverges. We just need to prove it. So we need to use a comparison test, and direct comparison is not going to work as well on this one because this series with its larger denominator is going to be smaller than this p-series down here. Showing you're smaller than a diverging series doesn't really help a whole lot. So instead, we're going to use limit comparison. To start that, I'm going to show that my original and comparison series are both positive. So my original is positive, and my comparison is positive, and that's going to be true for all n values 1 or greater. So now I just have to take the limit of the ratio of these two things. So limit as n approaches infinity of the original series over my comparison series. Multiplying by the reciprocal, I can rewrite this as radical n over radical 2n plus 7. And as n approaches infinity, I can ignore this plus 7 here. So this is really just like having the square root of 2n down here. I'm going to go ahead and split that up into radical 2 times radical n just to make my next step a little easier. Because on the next step, I'm just going to cancel these radical n's, leaving me with 1 over radical 2. Now the important piece here is that this number, this L we just found, is between 0 and infinity. This proves by the limit comparison test that our comparison series and the original behave the same. Since the comparison diverges, this shows by the limit comparison test that my original diverges. To figure out the convergence for this problem, I'm going to try comparing it to something that's pretty close to. This is almost a geometric series with these two exponential terms, but not quite. This plus 1 is messing us up. But if you think about it in the long run, this plus 1 really shouldn't make a huge difference for convergence. So I'm going to compare this to e to the n over e to the 2n. Again, just kind of pretending that plus 1's not there. And I could be a little bit clever here and take an n out of the numerator and denominator. So this is really e over e squared to the n, which is really just 1 over e to the n. So this is a geometric series. We have an absolute r value of 1 over e. And since e is a number bigger than 1, this ratio here is less than 1, which means that this series converges by the geometric series test. So we're trying to show basically that this comparison series and this other series behave the same way. To do that, we have to figure out which comparison test to use. If I want to use direct comparison, I'm going to need to show that my original series is smaller than my comparison series because my comparison series converges. You want to be smaller than a converging series if you're trying to show convergence. It turns out we can actually do that here. This 1 here makes the denominator bigger for the original, which makes the overall series smaller than the comparison series. So let me go ahead then with direct comparison. Now I need to also show that these series are both positive. So the way I'm going to show both of these things at once, both the positivity and the order that they go in, I'm going to say 0 is less than this original series here, less than or equal to my original series, which itself is less than or equal to my comparison series, which I'm just going to use this e to the n over e to the 2n because this is the most similar version to what I started with. And this is going to be true for n values of 1 or greater. Since I've showed this, and this is clearly true, that means that my original is going to converge by the direct comparison test. For this problem, to figure out convergence or divergence, I notice here that I've got something that's almost an exponential series, almost a geometric series. We have an exponential upstairs and downstairs. The only thing that's preventing us from using the geometric series test is this plus 1. But when you think about it, that really shouldn't make a huge difference. So I'm going to compare this to the series e to the n over pi to the n. which I can just take an n out of that and call e over pi to the n. This is a geometric series. The r value here, the absolute value of the r, e over pi, that is a number, since e is smaller than pi, this overall is a number that's less than 1, which means this comparison series is going to converge by the geometric series test. So that means that the original series should also converge. We just need to come up with the correct test to show this. So I have a choice between direct and limit comparison. Direct is usually a quicker test if I can finagle it. So the key here, since my comparison series converges, I would love it if my original series were smaller overall than the comparison. You want to be smaller than a converging series, and that would demonstrate convergence. If we look at this here, this plus 1 is making my denominator bigger, which makes the overall fraction smaller than the comparison. So we can use direct comparison. So what I'm going to do is I'm going to show that my original and my comparison series are both positive, and I'm also going to show the order that they go in, which should be original followed by comparison. So I can say 0 less than or equal to my original, which is less than or equal to my comparison, which I'm just going to write as e over pi to the n. And this is going to be true for really all n values here. N greater than or equal to 1, we'll say. So this shows by direct comparison that my original converges. For this problem, I'm trying to figure out if this series converges absolutely, conditionally, or not at all. So to start with, let me get a sense of what this series is actually doing, because sine is sort of a weird function to have in a series. If we plug in 1 for n, that would be pi over 2 plus pi, so 3 pi over 2. The sine of that is negative 1. Now if we plug in 2 for n, that would be pi over 2 plus 2 pi, so 5 pi over 2. And that's kind of the same as having pi over 2, so that would be positive 1. And then if I add another pi to that, I'm back at the bottom of the unit circle, and I'm back to negative 1. I add another pi, I'm back to positive 1. So this keeps alternating back and forth between negative and positive 1. So we can really write this as negative 1 to some exponent. But which exponent? Is it n or is it n plus 1? I don't know. Let me put n there and test it out. So if I plug in, let's see here, 1 for n, this would be a negative 1, which is what we got when we plugged in 1 for n over here. So yeah, this is the right way to do it. So now we're trying to figure out if this series converges absolutely, conditionally, or not at all. Let's start by considering the absolute value version of this, which is just 1 over n squared. Now this is a p-series, which we love to see. We have a p-value of 2, and 2 is greater than 1. Therefore, by the p-series test, this converges absolutely.